Morning. We can get started. So one of the little thing is, I think at some point I mentioned that some processes can get into the non-interruptible state and you can't kill them, right? Fortunately, unfortunately, the EXP06, the X Windows server is running in that state. So now it's a good way to actually look at it. So if you see the first line, the process 3247 is the one which is running. It's going in a tight CPU loop, right? It has 4 processors, so you probably don't notice it except when you go on the console, and I think it has some black or some blobs, right? You can't kill it, and the only thing you can try to do is reboot, and it still comes back to the same state. But whatever is causing it, most likely some hardware problems with the graphics card that the kernel would not let you kill it, and there's nothing we can do, right? And I mentioned that you may get into this state at some point, and we get to see that state. So if any of you wants to try to kill it by yourself or look at it, now is your chance before I try to fix that machine, right? So I tried to record the slides last lecture, but it didn't work. I mean, Microsoft has issues with the timing, for the audio part. So how are the homework projects and homework assignments coming along? You're doing fine? I'm sorry? I'm sorry? So today I want to continue back from where we left off, right? Before we do that, I want to briefly recap what we have done so far. In this module, we've been trying to look at synchronization primitives. So basically the idea is, if you have some data which is operated by multiple threads at the same time, unexpected things can happen depending on which thread gets to go first, right? So what you really want is put them into a critical section and ensure that only one thread can go in at any one time, right? And that's what we are trying to do in this part of the module of the course. And essentially, you need some support from the hardware, because if the OS is preempting your process halfway through, then you have no way of ensuring what your critical section code will do. So you need some kind of a hardware support, and we argue that writing it in the hardware is harder. So you write it using Semaphore, which may use a hardware mechanism to implement what it tries to do. So basically, you have 2 types of Semaphore, and they both let you say how many threads can get into a critical section, and the rest of them wait. Right? And then we said even that may be harder, so we moved to a higher level construct called monitors, right? Because one of the things you have to remember is all these locks, all these semaphores, all those things protect a segment of code, not the data. So if you forget to unlock, or if you forget to leave the lock in a good state before you get out of the critical section, or if you use the variables outside your critical section without protection, then bad things happen, right? So one of the ways you can avoid that is to say, make the whole procedure a monitor, and avoid making sure that the semaphores is unlocked before you leave. Semaphore unlocked our signal before you leave, right? So those are the different ways you can do the stuff. And today we'll start by looking at how you would implement semaphores and how you would use that to implement some of the classical problems we looked at, right? So is that clear so far? And the next section, after this, we'll go into the atomicity and stuff, which tend to be kind of involved. I mean, it's not hard, but I think you have to pay special attention to what it says and what it does and what it doesn't do, right? Which is sort of true for the Semaphore case too. So, one of the observations is when you look at Semaphore, right? It supports the operation of wait and signal, right? You expect the wait and signal to be atomic transaction run by only one thread, right? So essentially what you did was you moved the critical section from the piece of code that you had into the wait and signal, right? Because once you pass the wait and signal, you could potentially have many threads running, right? But you don't, because you're guarding it through the one critical section wait or signal. So you could argue that basically you made the problem simpler but not solve it. You basically moved the critical section from being a large code to this small piece of code. So you could implement the critical section using or the signal and wait using a busy loop, right? Busy waiting loop, because it's fairly small. But on the other hand, you may use a lot of semaphores. So you want to look at some mechanisms where you won't do a busy wait, right? Busy wait is not so much a problem on multiprocessor, like we saw in the server, right? Even though the server is fully using the CPU for the X server for one of the processors, for the most part we're all fine, right? Except your homework projects you won't get the 4 processors, but you're still making progress. However, on a single processor, you don't want to do busy wait. So that's the algorithm we'll look at next. So we want to look at implementation of semaphores with no busy waiting, right? So the way you do that is to have a mechanism for the thread to give itself up, give its CPU up, right? And have a mechanism for some other thread to restart a thread. So the way you do that is you have 2 functions, block and wake up. Basically, if you implement a block, that means you give up your CPU, you put yourself in some sort of a wait queue, right? Waiting for the semaphore. And wake up, you give a process which says that process which is waiting on a blocked queue should be restarted, right? So those are the 2 primitives that we need. So when we hit a point where you have to busy wait in the previous implementation, you would call the block, right? And in the case where you would signal, if you find that there's another process waiting, you can wake that up directly and let that continue, right? So for implementing the semaphore, you need 2 variables. One is the value that we looked at before, which is depending on the semaphore value, you initialize that to whichever one you start with, right? And then another queue which has the list of threads which are waiting for the semaphore, right? And you can use that list to the wake up call to see who should run next. So essentially, the code remains sort of the same like what we looked at before, right? The wait semaphore would keep decrementing till the number gets to 0, and if it's 0, then in the previous code we looked at, we'll do a while the condition is not true, you do a loop. Over here you do a block, which means that you tell the operating system you're giving up the CPU. There could be a context switch, right? Some other thread could run. So the thread which has the signal when it finishes, right? If it sees that somebody could be waiting, it wakes up that process, where the P is the one that you get from the next data structure, right? You figure out which one should run. Depending on the particular implementation, you may choose different threads to restart, but essentially you restart the stuff, right? So this is good in one sense and bad in another sense. It's good in terms of you don't waste any CPU while you are blocking, but it's bad because you have to do a context switch, right? Context switch means you're bringing a new thread and you lose all the context and everything. So if you expect to be waiting for very little time, you would like to do a busy wait. If you're expecting to wait for a while, or if you're on a single processor, then a block system call may be useful, right? And modern operating systems tend to have data structures which can do both. For example, Solaris calls it adaptive blocks, where depending on how many instructions it expects, it can either put you to sleep, do a spin lock or block. We'll see that in a few slides. But essentially, you could have a variant where you can do both depending on what you're trying to do. And I talked a little bit about deadlock and starvation before, and we'll talk a whole lot about deadlock in the next chapter, right? Essentially, the idea here is, so if you have multiple threads, right, not all threads get to run all the time. So some of them may not get the amount of CPU that they require for fairness issues. So the two notions, starvation and deadlock, differ in what could possibly happen, right? With the starvation, the particular thread is not getting enough CPU, right? So it may be waiting for a long time. It may starve, but it's not deadlocked. The notion of deadlock is you enter a point where nothing can help you, right? However much, even if you let it run for infinity, this cannot be broken, right? So for example, the piece of code over there, and suppose you imagine the two semaphores S and Q to be set to 1, right? Depending on the order that the process 0 and process 1 are running, right? Both of them want both the logs, but the order in which they request it means that processor 0, they can both start run simultaneously. Processor 0 can get the semaphore S, and processor 1 can get semaphore Q, right? At this point, they're deadlocked because they both want the opposite, the other semaphore, right? So they both cannot release it till they finish this code and release it. So they are in this mortal deadlock where nothing can break out of this because they both want the other resource, right? So process 0, if it was made to, if it could finish what it's doing, it'll release both the logs and then the other one can run. Similarly for process 1. But in this case, both of them hold one log and they want the other stuff, so they cannot ever finish, right? And we'll see how you'll notice it and what conditions have to be met for deadlocks to happen. But essentially, when you have a deadlock, there's usually not much you can do, right? Whereas in the case of starvation, it may just be, so if you have a very low priority and you never get to run, right? That's a form of starvation where you're not getting a fair share, right? You're not getting to make progress, but there's inherently nothing which prevents you from making progress. It's just that there are many more higher priority processes, so you don't make progress, but progress is still possible, right? In the case of the dining philosopher problem, when you add the notion of eating and stuff, right? So if a philosopher never gets to eat because both the other two people are fattening themselves up, right? It basically means that you starve, but you don't have to necessarily deadlock, right? So we'll look at how you would implement the dining philosopher's problem using monitors, right? Monitor basically says that if you put these functions in a monitor, then only one of them gets to run. So you don't have to have a explicit semaphore to lock and unlock before each of these segments, right? So remember the dining philosopher. There are 5 philosophers, and they have a chopstick or a fork on each of their sides. They need to have both of them to eat, right? So if they hold on to one and wait for the other, right, there's a potential for deadlock. We'll see precisely how that happens in the next chapter, right? But you can imagine how that happens, right? If I take my left fork, and every philosopher does the same thing. They take the left fork and then they're looking for the right fork, right? They all take the left fork. So if all of them ran instantaneously, then all of them have their left fork, all of them are waiting for the right fork, and you have a deadlock, right? So what you want to do in a solution here is, I try to take my left fork, I try to take my right fork, right? If I have both the forks, then I'm good, I get to eat. But if I try to take my left fork and nothing happens, I put it back, right? I put it back and change my state to say I'm still hungry, right? So I define 3 states. One is I'm thinking, one is I'm eating, and then I define a state called hungry, where the philosopher wants to eat, but it can't get these 2 forks, right? So it has to wait. So you define that notion, and the other notion is, if I try to take a fork and if I can't use it, I put it back, right? So it's possible for somebody else to make progress. So the two functions we use to implement the learning philosopher problem is the pickup and the put down, right? So pickup, you try to, and you can only eat if both the people on your side are not eating, right? Which essentially means that both of them don't have the fork with them, right? So if you look at the state of both the philosophers on your side, if they are hungry, that's fine, but if they're eating, that means they have the two forks that you want, which means that you should be going to the hungry state, right? So to pick up the fork, right? So the philosopher who wants to eat wants to, so first they set their state to hungry, right? So they want to eat, and they want to see what's the status of whether they can eat, right? And I'll show in the next slide what this test function would do, right? The test function basically sets the state of what I'm allowed to do, right? What state I should be. So if testing set the state of myself to be eating, right, that means that I'm supposed to eat, so I get to eat. If I'm not eating, I put myself to wait because I'm still in the hungry state. So I start off with the hungry state. I check to see what state I could be by looking at both my neighbors. And if they still suggest that I should still be hungry, I wait, right? And we'll see what the code for test in the next page. So when I'm done eating, right, I change my state to thinking, right? And again call the test for both my neighbors, which basically would set the state, basically would set the state for those two neighbors, right? So they all operate through this function test, right? So I call it for I plus 1 plus, percentage 5. Basically, you're trying to do the left and the right neighbor, right? So basically, you go through a loop where you try to pick up, right? And then you eat, and then you put down, then you think, and you go on a loop forever. Right? So the code for test looks sort of ugly, but basically what you're trying to do is, so you're trying to test what is the state that a particular philosopher can be, right? So there are three conditions. One is so you're trying to see if the state can be in the eating state, right? I can only be in the eating state if I'm hungry and the left one is not eating and the right one is not eating, right? So basically that's what you say in the if loop, right? You look at the left using the I plus 1, mod 5, and then the plus 1 mod 5. So basically look to the left and look to the right, see if they're eating. If they're eating, and so if they're not eating, right? So if the left one is not eating, right one is not eating, and I'm hungry, that means I get to eat. So you set the signal, you set the state to eating, so it says that I can eat, and then you signal myself, right? So if you go back over here, right? In the first pickup case, I do a test on myself, which means that I'm hungry, I want to look at what's in the left, what's in the right. If one of the cases is not true, I would come here and then I would wait on the self of I dot wait, right? And when both of them finish, right, the test would set myself to be eating, and will signal me so I can proceed, right? So either I go through or I wait on the wait signal, right?
That's right.
Yeah.
We talked about this last class a little bit, but so essentially, does like a monitor just like a high-level implementation of semaphores typically then? Or?
Yes. So one of the way I look at it is they are built a hierarchy of how useful or easy it is for you, right? They all essentially build off of a hardware implementation because hardware has to provide some support. And then you have a notion of a semaphore, right, which is basically API around the hardware implementation, right? Monitor basically internally would use a lock or semaphore for the whole function, right? The reason why we need monitors is if you were to implement this using semaphore, right, you would have semaphore protecting the whole segment of code. So you'll have one at the top, one at the bottom kind of stuff, right? But sometimes people, so if you don't unlock the semaphore when you should, right? If you just do a return, if you do an exit without unlocking the semaphore, then your program would behave badly. It can lead to all kind of states, right? So the notion of monitor is to prevent you from yourself. So it's basically, it says that you don't have to worry about locking and unlocking. If you call a function as a monitor, then I basically put a monitor up in the front, when you start the execution, and at the end, regardless of where the end is. So if you exit out of it using return, what have you, when you get out of the function, I'll make sure that the stuff is unlocked. So yes, monitor is the same as the semaphore, right? Because that's what they implement, and that's one of the reasons why I said it's not necessarily as trivial as that, because it depends on what you're trying to lock, right? So when you use the Java model or Java synchronized code, right, you have to understand that underlying Java uses a lock per object, right? So when you do a monitor, it depends on the instantiation of the object that you're operating on, not on the class itself, right? So you have to do this. The lock belongs to this, right? If you know Java, it belongs to that one, right? So, but does that answer the thing? So they're all the same, but depending on which one you're more comfortable, more useful. The assumption is monitor is supposed to be easier, right? Because you don't explicitly have to worry about locking and unlocking. Except in this code, I do talk about signals and weight. So, right. And the initialization code basically sets everything to thinking, right? So is that clear what this segment of code does and why it should work, right? So this is one way of, one example of how you would implement one of the classic problems we looked at before using semaphores or monitors. The book has a little bit, I think one more case on how to implement that using semaphores. And of course, you can solve that for every problem we looked at, reader, writer, or bounded buffer, or what have you, right? So I'll briefly talk about some of how the different operating systems implement synchronization, right? So the first thing is we look at Solaris. Solaris is we look at Solaris because it's a highly scalable operating system. It scales to thousands of processors. So it has to have a good way of doing the locking, like in a higher performance. So naturally, it implements locking, semaphores in a number of different ways for a number of different stuff, for multitasking, for real-time systems, and all those things. So it basically supports this notion of adaptive mutex, right? So it can figure out. So if it knows how much time you would wait, then it can either do a spin lock or it can do a blocking call, right? And so it goes through mechanism to figure out how much time it hopes to wait, how much time the process should wait, right? And it kind of rings like the one we talked about before when you're trying to do scheduling, right? So if I know how much time I'm going to sleep, then I can do a good job. But operating systems typically do not know how much time it will take. So if you can do that, then adaptive mutexes can potentially give you a better performance, right? So if you are a multiprocessor machine and you expect to sleep for a few instructions, then you would want to do a spin lock. But if you're in other cases, then you would want to do a block and let somebody else run, right? And it also supports the notion of turnstile. So the other issue you need to worry about is who keeps track of what threads are waiting for each lock, right? So we talked about this abstract data structure called next, and which figures out which thread is waiting, and who has them and who manages them is an issue that you need to address, right? Obviously, it's a structure that the kernel has to know so it can figure out who should run next. The way Solaris does that, it calls turnstiles, right? Turnstile is a queue per, it's actually data structure per mutex, right? But a turnstile is initialized for a thread. The assumption is a thread can only be locked on one particular object at any one time, right? A thread cannot be blocked on two things at the same time. So you associate a queue with each thread, right? And you use that to implement locking on an object. So the first time an object blocks, it inherits the turnstile of the thread which it blocked on, right? And it uses that turnstile for the rest of the threads which are going to wait, right? So these are implementation issues that you need to worry about, how to efficiently manage these things, because you don't want to have lots of data structures, because if you have a lot of data structures, then you have to search through them, allocate them, and I hope you appreciate the O of 1, all those things we looked at scheduling. You want to make sure that the things can be searched quickly, so you associate data structures such as it's compact and it's easy to search for, and the way it does that is through this notion of turnstiles, right? On a more normal processor, like normal OS like Windows XP, which is not necessarily running on multi-processors as much as you have with Solaris. So they implement semaphores by turning off all the interrupts. So when you go into a critical section, you turn off all interrupts, which means that you basically go into a non-preemptive mode, right? And when you're done with the semaphore, you go back to being a preemptive kernel, right, on a single processor, because that's good enough to solve the problem, because there's no way to interrupt these processors. On a multiprocessor, Windows XP uses spin lock. So basically, you'll go in a CPU loop waiting for the event to happen, right? It does provide mechanisms for you to do the blocking call using what they call as dispatcher, right? And events, so you basically send an event to a dispatcher, and it operates similar to your wait and signal. So you send it operates the incrementing and decrementing functionality of a semaphore using events and dispatcher objects, right? And Linux, I'm not going to go through more of Linux now, because we'll spend more time on Linux at the end of the module, right? So it disables interrupt for small critical sections. It provides semaphores, spin locks, more later, right? And pthreads library, as you may be looking into it for your homework project, it provides an OS-independent notion of mutexes and condition variables, and also extensions which are non-portable but gives you better performance, right? Pthreads, the main claim to fame is it's portable across different machines. So if you're trying to go for portability, sometimes you lose on performance. So they provide extensions where you still get the benefits. So you can still do spin locks if you want, and not use a generalized notion, right? So these are different ways of doing the synchronization. So together, right, these give you ability to mark a piece of code as critical section such that only one thread can run inside it, right? So is the notion fairly clear at this point? So that is all I had for this lecture segment, right? So since we're kind of early, I want to go to the next section, right? But I want you to be clear on the semaphores and the monitors, because the next section builds a little bit on top of that, right? So we introduced the notion of atomic transactions, and this is the section I said, some of the stuff we talk about, it's fairly important you understand the exact details, right? And the notion of atomic transactions basically comes from databases. So I'm not sure how many of you have taken a course in database, which is usually offered in the senior year. You taken a course? Right. So if you're taking a course in database, this is all old stuff, right? If you haven't, you'll probably take it in the future. And this is their bread and butter. The only catch that we look at here is databases are more worried about the consistency of the data rather than speed, right? When you're working inside the operating system, you're worried about the performance. You're not worried about, you want to give the database functionality without paying the full cost of what a database can do, right? So when they try to implement database functionality within an operating system, you want to be aware of that restriction, right? And throughout the history of operating systems, there's been back and forth on should the database be part of the operating system or should they be outside the operating system, right? And it's never really solved, because one of the camp is the users really want to get their work done. So they don't really care whether it's in the operating system, whether it's in databases or what have you. So if you put it inside the operating system, then they can be happy and everybody's good to go. The other argument is if you put it inside the operating system is slow for everyone. Right? So if there exist people who don't really want the functionality, they're going to pay the price for it by having a slower operating system. So do you want a screamingly fast operating system which does not do much and you put the stuff on top of it, versus do you want an operating system where it'll do everything for you, right? And this argument goes back and forth, and it's not clear which side wins. I think a pragmatic mix would be what most of them follow, right? I think when Windows Vista supports a lot of transaction functionality into the operating system, right? Which is similar to what VMS did in 70s and 80s. So history repeats itself. So let's look at what are the challenges and what are the operations we're talking about, right? So first, we define a notion of a transaction. So all these databases define a notion of transaction, which sort of relates to the critical section we were talking about. So transaction is a set of operations which together form one concept, right? And you expect it to be all or nothing, right? So for example, if you're taking money from your checking account to a savings account, right? So the set of operations you may do is you may take money off of a checking account and move it into a savings account. They're both part of one transaction, right? You as a customer do not want the transaction to be run in half. You don't want the case where money is taken out of your checking account and then the operation stops, right? The banks probably won't care, but you would be out of money because the money came out of the checking account but never made it into the savings account, right? So the notion here is both of them have to happen or none should happen at all. You cannot have something in the middle, right? And this is true for most of the operating system stuff that you do. You have pointers, you have queues, so you cannot take a process out of a queue and not put it into somewhere else before you leave. It's not okay to take a process out of a queue and then go away, right? So there's inherent notion of a transaction. What you do about it, how far you go with that is what we're trying to look at here, right? So transactions, it's important to remember it's all or nothing, and the boundaries are defined by application, by a user, right? So transactions can be fairly long or can be fairly small. And typically, when you're talking in databases, transactions would be fairly long, right? Because you're worried about functionality of the application, what you want to gain with it. When you want to try to do it in the operating system, you want to keep this transaction as small as possible, just because you want the system to be manageable, right? So if you're trying to register for a class, and if it takes you half an hour to do a transaction, that's okay in databases, not okay in operating systems, okay? So once you have this notion of transaction, so basically what you're saying is you allow a set of operations which operate on data, which changes something in the system, right? So before you start a transaction, you have to say, this is where I start the transaction, and I proceed, and this is where I end the transaction, right? At that point, we call it commit. We basically say something to the system to say, this transaction is completed now, it's committed, right? If for any reason in the middle you have to break out of the stuff, you call that abort, right? So you say the transaction is no longer valid. So when you do abort, you want the system to behave as if nothing ever happens. You want the system to roll back to where the system was at the time you had you started a transaction, right? So essentially, you start a transaction, you make modifications to the variables in the system, right? If you do abort, everything gets put back to where they were. If you went to the commit point, everything stays. Whatever transactions you made stays, right? When you talk about databases, they'll call a property call ACID, and the atomic, consistent, two other terms, right? So basically, you talk to make sure that these properties are fully validated. The other property that you want to maintain is if there are two transactions operating at the same time, transactions do not see uncommitted data, right? So if you're making modifications till it's committed, it's not seen by others, right? If you use that in the operating system world, what that means is I could be changing data structures, and till I'm finished, nobody else can see what my change is. And when I do a commit, instantaneously it changes to the new value, right? So I may do lots of operations. I may be changing this variable, changing a whole bunch of state. When I do a commit, everything happens, right? Nobody can see something halfway through, right? Which sort of means that at the point when I'm committing, the whole system has to stop because the other threads cannot make anything to look at the data inside the transaction, right? So those are the notions. So there's a notion of a transaction, notion of a commit, notion of abort, and notion of a rollback. Rollback would go back to where you were, right? Go back to the state when the transaction started. So to implement a transaction, first you need a notion of volatile, non-volatile, and stable storage. We haven't really talked about storage yet, right? But you know the sort of the notions of what you're trying to do, right? Non-volatile storage is something that doesn't survive system reboots. Volatile is opposite, right? Volatile is something that does not survive system reboot. Non-volatile, survives system reboots. And stable storage is what the theory would talk about. We talk about database storage. Stable storage is what you talk about, where it's a form of non-volatile storage, but you expect it to be there forever, right? And in a real database system, you do replication, you make multiple copies and stuff to make sure that stuff stays, and you spend a lot of time trying to make sure that what you call non-volatile can actually implement a stable storage, right? Non-volatile is not stable when the disk crashes or something goes away, right? Stable, expect it to stay forever. So what we really want is something where if you write something into it, we can be sure that it's going to survive, right? That's the notion of stable that we really care about. So let me start the discussion on how the transaction really works, right? So we use what is called log-based recovery. So we use a data structure called log, where you keep writing data and you can take data off the back, right? So every new transaction, every new operation, you log it, right? You append to the end, and it keeps growing to infinity, right? So when you do a transaction, right? When you do a write operation on the data, you log it, right? You log everything that you need to undo the stuff later, right? So you log the transaction name, which helps you figure out what are the operations which are part of a transaction, right? You log what variable you operated on, what was the old value, and what's the new value, right? So if you were to somehow start back again, you can replay it again, right? So you can replay the logs over and over again from the same starting point, and things will be the same. In fact, there's a property that you want. It's called idempotent, right? So if you start from the same location and you repeat the log over and over again, you should see the same effect over and over again. If you can't enforce that, then you cannot implement transaction this way, right? So for example, if you send something to the screen, I can't take it back. If I can't take it back, then you're seeing the effects of a part of a transaction. It's not good, right? So you want the stuff to be idempotent. So you want the stuff to be able to replay it all the time, right? So when you start a transaction, you write something into the log saying start of a transaction and the transaction name. And when the transaction finishes, you write transaction commit, right? And since it's a stable storage, you don't have to worry about whether it goes to the disk. Magically, if you write into stable storage, it's always there for you, right? So if you were to abort in the middle, right, which means that you have to redo everything. So you have to go back to the state where you were before, right? So you have to you have to roll back the logs, right? So you have to go in the logs and look back at all the operations and undo everything back to the where they were, right? So from now, you go back on all the logs and figure out all the operations and undo all the values so that till you go back to the start of the transaction, right? And the system can proceed from that point as if nothing happened, right? Is that clear? So every operation that you do, you store what the original value was, what the new value was, and you keep proceeding. So your system is going to be slower now. So you're going to do writes to this stable storage, you can't proceed till the write is finished, right? And now if you have to abort for any reason, you go back and replace all the values to what they were atomically, right? While the log is replaying, you cannot let the system run. So you go back to the state, and hopefully from that state on, you proceed, right? So depending on how comfortable you are with this may be godsend or this may be horrible, right? So it may be godsend if you're looking at you're inside the kernel and you are trying to operate on data structures, right? Like I said, the PCB on Linux is 1.7 kilobytes or something. It's a fairly large data structure, right? You're operating on this data structure. You're moving pointers. You're adding stuff. You're doing whatever. If something happens in the middle, you can either make sure that you undo everything you did so that the data structure is back the way it was, right? You can write the code yourself, and in which case there may be errors. Somebody may add a line of code which they didn't undo, kind of stuff. If you had transactions, then basically you would, before you write the code, you say transaction start, right? And at the end you say transaction commit, right? So you would add some piece of code which says transaction start, transaction commit. And if you have to get out anywhere, you would say transaction abort, right? And magically everything goes back to where they were, right? So I'm not sure what camp you would be, but depending on, if you think about it, right, you can argue that this, having this facility inside the kernel is a really great thing, because now you can freely operate on stuff and just call abort, and everything is way back they should be, right? The other argument is, you may hide the stuff from me, but basically you still have to, somebody is paying the price for all this stuff, so, right? So it's a philosophical argument. It's very similar to the argument of, do you need monitors? Can we just live with Semaphore, right? So how many of you know the notions of databases in general, not necessarily in a class setting, but used it in some form? For class? What class?
We took Ramsey's database course last semester.
Okay. But that's offered in the senior year, right?
They offer the junior as well.
Okay. So if you took the database course, you might have seen all the stuff, but the main difference here is, database course, you are really worried about the consistency of the data, right? You don't really care about the performance so much because it's a different world. I mean, it's assumed to be add-on, and your data is more important. Over here, performance is everything, right? We looked at why O of 1 scheduling and all those things are important. So if you're trying to get the last byte of performance out of the system, maintaining all these structures is not considered to be, some people don't like it, right? The sort of people who won't like it is, if the logging would do everything that I have to do, then it's, I would like the operating system to do the work for me, right? But sometimes I, as a programmer, may choose not to undo something because I know that nobody really cares, right? So for example, if I have data structure which keeps the time that some operation was done, right, in one of the fields, which is part of a transaction, right? I may not undo it as a programmer because, yes, the value is not what it should have been, but it doesn't really matter. It's just a logging value. So I, as a programmer, may know that some values have to be unrolled, some values don't have to be unrolled, right? And the argument is, OS can't do that. Yes?
When a transaction is aborted, how do you know how far to roll back? Is there a marker that says this is the last consistent state? Or?
So I haven't talked about the optimization yet, right? No, basically you have to go back to the transaction start, right? Every time you do a transaction start, so when you do abort, you have to go back to the start of the transaction, and you go from there, right? There are optimizations, and I don't want to touch that here. Basically, you can do a checkpoint. You can say, at some known state, I'm consistent. I don't have to do this stuff, right? And so the reason why you do this optimization is there are multiple data structures. There's some stuff in the main memory. There's some stuff in the non-volatile store and stuff. The only stuff we know for guaranteed is the log structure which is in a stable storage, right? So when you do a undo, right, stuff may be all over the place, so you have to make sure that it's undone everywhere. But you can optimize it by saying at frequent intervals, you can checkpoint to say, at this point, I make sure that everything which is anywhere goes into stable storage, and then I can say, I can go back to that state and things will be fine, and you pay a price for that, right? When you have to do this checkpoint, then the system slows down because when you're doing a checkpoint, everything has to stop while you write the state to the disk, right? So I don't want to continue to the next parts of where we are going with this stuff, right? But the notions of transactions and stuff, we'll use that to, essentially what we're trying to build is, when I say there's like multiple threads and then there's one thread going through here, right? If you want it to be non-deterministic and say one of them can go and you don't know what the order and all those things are over here, I don't want to say anything about the interleaving, then what we have so far is good. What we're trying to figure out is, can we say something about what should happen here? Can we say something about what should happen here? Even though there may not be any data sharing, right? I want some consistent output, so I want to be able to say which happens what, so I can say how a program behaves. And that's the notion of serializability, which we'll get to. If you're taking databases, many of them may be going back to the same concept, but that's what we'll go from here in the next lecture. Okay. So that's it. I'll see you guys on Wednesday.